Hi everyone, and welcome to lecture 12 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vechev and I'm professor at ETH. And in this lecture 12, we're going to be discussing a new method for certifying robustness of neural networks that comes with statistical guarantees called randomized smoothing. Okay, so before we start with the method, let us remind ourselves of the deterministic certification methods or the certification methods that we looked at so far in the lectures, in some of the previous lectures early on in the course, before we started looking at certified training, training with logic, and so on. Okay, so what you have with the standard convex-based certified verification is that you are given a specification. Okay, we're given some specification. This could be, for instance, an L-infinity bow around a given image, or it could be some region that captures the parameters of the transformations, like rotations and translations and so on. And then what we try to do is we try to push that symbolic region through the network for these abstract layers, these layers now which have abstract effects because they need to transform shapes rather than concrete values. And so we push these things through, okay, we push them through, and we obtain this intermediate invariance, symbolic invariance in the middle of the network after each layer, okay? And so to balance precision and scalability, we looked at different kinds of convex relaxation. So for instance, the box convex relaxation, the deep poly relaxation, the zonotop relaxation, and each of them tries to balance this trade-off between how big networks it can scale versus how much it is actually able to prove, because these are necessarily incomplete methods, all right? Okay, so the advantage of this general method of propagating the symbolic shapes and in general is that it is quite general method, right? So it can prove any safety property. It is not restricted to just robustness properties. So if you give it an arbitrary pre and post condition, then you can use those methods to prove those properties, okay, out of the box. Another advantage is that these methods provide deterministic guarantees. So when they say that something is verified, it with 100% certainty means that it is verified and the property holds, right? And in general, this is an active area of research where different researchers are trying to come up with variants of these convex relaxations in trying to handle bigger and bigger networks, right? And with higher precision, okay? So the limits of these methods are still kind of unknown because researchers are training specific networks with high accuracies potentially that you can verify with those methods via specific certified training schemes, or just coming up with new convex relaxations that scale and are precise. Nonetheless, those methods are somehow limited by the depth of the network, okay? So the deeper the network is, because of incompleteness, those methods, as they push these symbolic shapes through the network, through the layers, they are going to incur more and more imprecision. So when the network is very deep, it may be difficult to prove properties when they get actually here to the final shape, the brown shape, okay? So handling bigger and bigger networks is definitely quite challenging for these techniques. And this motivates us to look at other kind of certification methods which relax these deterministic guarantees and perhaps the generality of properties that they can handle, but they may be able to scale to larger networks. So they capture a different point in the design space, this certification methods. And in general, it is good, it's important to be exposed to all of these techniques so that we have more techniques to prove properties about our models. Okay, so let's take a look at this method. So the name of this method is randomized smoothing that we're going to be studying today. And right, so what is the key idea behind this method? Well, the key idea is that we're going to be given some classifier f. Okay, so we're going to be given some base classifier f. And then what we're going to do, we're going to construct another classifier G out of this classifier F in a way that G has certain statistical guarantees, statistical robustness guarantees, okay? Now the construction itself is deterministic, but the guarantees that G will provide will be probabilistic guarantees, okay? And these probabilistic guarantees are going to be holding with high confidence, with high probability. So there are several advantages of randomized smoothing, which is that the construction does not assume any knowledge about F, okay? So doesn't care really what F is, but we'll see in practice that actually it matters a bit what kind of F you get, so that you get better guarantees out of G. Now, a major advantage of smoothing is that it can scale to large networks, okay? That scales to large networks. It doesn't involve propagating the symbolic shapes through, which is one of the reasons why it scales, okay? Now, the method focuses generally on restricted robustness-like properties. So you have a point X and you have some region around X, right, that you want to certify. So perhaps not as general as the just taking arbitrary safety properties as the convex methods, but in the space of robustness, we are interested in this, in robustness properties. If we're considering proving robustness, okay. And another point about this method is that it requires sampling at inference time to evaluate G, okay. As we'll see, you need to sample more than just running the input point X through, which is something that the convex methods do not require. But still, this advantage of scaling to larger networks is important, and we want to be able to know how to use this smoothing so that we can scale to larger networks when the convex methods are not able to. And also here we have the standard accuracy versus robustness trade-off that we saw before in our earlier lectures when we were discussing adversarial training, okay? So we're going to be closely following today the presentation of randomized smoothing, as is in this paper, which came out last year, okay? Randomized smoothing was actually introduced before in other papers, but what's nice about this work is that it produces tighter certificates of robustness than prior work does. And this is why we're going to be following it in our lecture today. And then you can, of course, if you have specific questions that involve the appendices, for instance, somewhere you can look up the PDF here. Okay, so let's get to this. So let's look at the construction and what we have here, okay? So we're given this base classifier F. So we're given this base classifier F, and the base classifier F, as usual, takes some points, some vectors in RD, so images in RD, like a CFAR10 image or MNIST image or ImageNet image, and classifies those images to a particular label, okay? So how does the classifier, the smoothed classifier G works? Well, let's look at the definition here. So what happens? Let's look at it from the inside out. So we're going to be given this isotropic Gaussian, okay? Isotropic Gaussian is just the Gaussian distribution here with mean 0 and the covariance matrix being the variance times the identity matrix. Okay, so we're going to be drawing noise, epsilon is going to be distributed according to this isotropic Gaussian. So we're going to be drawing noise from this distribution, okay? And then we're going to be invoking, so we are given an input X, okay, to the classifier, and then we're just going to be invoking our base classifier with this X, but with some noise added to this X, okay? Okay, fine. And then what are we going to be caring about here? Well, we want to know what the probability is of feeding X perturbed by this isotropic Gaussian noise is of producing some label C, okay? So we want to know how to do this, how to obtain this probability, okay? And our goal will be to find, okay, the label C. We're going to find some label, okay, some label that we return, searching among the label C inside this Y here, in the Y set, which gives us the highest probability. Okay, so it's going to give us the highest probability. We're going to find the label that gives you that has the highest probability when X is perturbed with this Gaussian noise. Okay. All right. Another way in which you can imagine this working is if you have the Gaussian distribution with the mean being X and the variance being sigma squared, you are trying to find the label which has the highest measure under that distribution. Okay. So if you take the region under that distribution which has the highest measure, you return that label. Okay. Now, of course, this definition here, it's all good, but computing this thing in practice, right, is infeasible, because essentially you need to integrate over the noise, and solving this exactly is just practically infeasible. We'll discuss this a little bit in later slides. So we'll need to employ some form of approximation to solve that integral, to compute this argmax here, and hopefully by having some guarantees on the approximation. Okay? But this is the definition of G of X, and this the standard deviation sigma here, okay, controls the amount of noise that you introduce. So the larger sigma is, the more noise you will introduce. Okay, so let's move on here and discuss a little bit about what are the guarantees that this G actually provides. Okay, so let's look at the guarantee, what we have here. We're going to explain this guarantee in the follow-up slides. Okay, but just for notation purposes here, we're going to have some label C of A, okay? And we're going to have some probabilities, PA and PB, that are lower bounded and upper bounded respectively. And then just, we're going to explain this in a second, but let's just look at a little bit at the two parts. So essentially what it says is if you satisfy this condition, which is trivial, then what the important part is here is that from the Gaussian noise that you introduce, you can obtain a certification radius. This is the L2 norm, just to be clear, it's not L infinity norm. So you're going to end up with a certification radius, okay, around the point X, which the radius has certain value, but this value of the radius is controlled by the parameters of this isotropic Gaussian, okay? So we're gonna look at this, what exactly this is in a second, but the important thing is that from that isotropic Gaussian and the standard deviation sigma, we can derive essentially a certified radius around the point X, okay? So let's look at in the next slides to see the components of this guarantee so that we can understand it better, because we are going to be needing this theorem that is proved in the paper in more detail, and we are going to look at the proofs of this theorem in the exercise. Okay, so let's look at it a little bit, what is happening here, and break down this theorem. It's actually not that bad. It's actually pretty direct what it says. Okay, so first let's look at the first part over here. So what we have, really what it says here is we're going to have some label C of A, we're going to have some probabilities here. And what are these lower bounded probabilities, upper bounded probabilities? What it really says is, first of all, you know, what this whole line here says is, first of all, C of A is going to be the most likely class, okay? It's going to be the most likely class. And the probability of C of A, which is P of A, okay, is going to be some P of A, and we're going to have some lower bound on this probability of P of A, the lower bounded P of A here, okay? And then that, of course, if I plug P of A here, this is also going to hold. okay? And then this lower bound on the P of A, okay, I want that to be greater than, kind of obviously, to the upper bound of the next highest label, C of B, okay? That's what this really thing here says. Let's just take the probability of the next highest label, okay? So this is the probability of the next highest label, P of B, okay? And let's just take an upper bound of that probability. Maybe we'll take a value that is slightly greater than P of B. Of course, if you plug in P of B here for the upper bound at P of B, we would still get a valid constraint here. So all we just want to say is that, well, let's take the most likely class C of A. Let's take a lower bound on its actual probability, okay? Let's take an upper bound on the probability of the next best class. Here is the next best, the probability of the next best class. And that's all it says, okay? So of course you can instantiate this here with just P of A and PB, but we need this underscore PA and, lower bound on the P of A and upper bound on the P of B because we're going to be estimating those later. So that's why we write it like this right now. Okay, and this is what this says. This is a lower bound on the true highest probability P of A, and this is an upper bound on the true second highest probability P of B. Okay, so let's say that you can obtain that, which sounds reasonable. Okay. Now, one question is how can you obtain this? Okay, so in theory, if you actually have a very small classifiers here, F. Okay, if you have very small classifiers, you can actually compute the exact probabilities, PA, PB, by just using an exact inference solver like we've built called C. This is a widely used solver that we've built by various communities. And you can just give it this isotropic Gaussian for the epsilon, right, being distributed according to the isotropic Gaussian. You can give it the, the function F, which is the code of the classifier F. And then you can feed it from C and obtain the probability distribution over the output probability distribution of F, which is invoked with X plus this epsilon distributed according to the isotropic Gaussian. Okay, and then you can take the argmax there of that distribution and obtain your exact PA/PB. Okay. Now, the problem is, even though this would work for like small models, it's extremely expensive, and really these exact inference solvers will not scale to this kind of realistic networks F that we want to be looking at, which is the whole purpose of looking at smoothing in the first place. Okay, so instead of doing that, what we're going to be doing, we're going to be estimating those probabilities. We're going to approximate those probabilities underscore PA and upper bound on P of B. And we're going to do that. We're going to estimate these guys here, okay, with certain statistical guarantees, okay? That's what we're going to be doing. But this is the first part of the theorem. So if you can obtain this PA/PB with these constraints here, okay, then you can invoke the rest of the theorem. So this is the condition, the precondition, and now when you have it, you can invoke the theorem with what follows. Let's look at what follows. Okay, what follows is that it tells you that you're going to get this robustness radius. Okay, that is, okay, so let me just highlight it here. Okay, you're going to get some robustness radius, which is computed, L2 robustness radius, which is computed as follows. So you're going to get certified robustness radius around the point X, okay, which is obtained as follows. What are those things? Well, we just take the PA/PB, the lower, just not use it here. We take the lower bound on the true PA, take the upper bound on the true PB, and we feed it to the inverse Gaussian. This is the inverse, of the standard CDF, Gaussian CDF. So standard Gaussian CDF, right? So standard Gaussian, the mean is 0 and the variance is 1. Okay, so that's not to be confused with the isotropic Gaussian. Okay, from the isotropic Gaussian, we just take this sigma, the standard deviation here. Okay, so the bottom line is once we have PA/PB, we can actually obtain the radius, and we have that sigma, we can obtain the radius, and this is your certification L2 certification radius around the point X, which is great. Okay, that's what the theorem tells us. But let's notice like just a couple of points here. What happens, just a reminder. Okay, so if X is distributed according to the normal Gaussian and P is some probability, okay, then this, okay, the inverse CDF, when it is invoked with this probability P, is going to give you a value V, right, such that the, of course, the probability that X is less than V, less than or equal to V, is P. Okay, so just the meaning of the inverse CDF, okay? One thing to note here, which is a little bit helpful when we're discussing later the proof sketches, is that the inverse Gaussian phi minus 1 here is monotone. Okay, so higher values of the probability will produce higher values for the output of the inverse Gaussian or inverse CDF. Okay, and this is useful property to know. Okay, now a couple of points here before we start looking at guarantees. Okay, is that if I fix the noise sigma over here, right? If I fix it like in my isotropic Gaussian, I just pick this noise level, okay? Then how can you increase the radius R? Well, the only way to increase the radius R is by having these different PA/PBs here. So what we would want is to have a higher PA and lower PB, right? This follows from monotonicity, right? Okay, this is helpful here. So higher PA and lower PB is going to give me greater and greater radius R, which is what I want. I want to get a better radius. Okay, so I'm more robust. Of course, how would you actually get this lower, this PA and PB to be higher and lower? Well, we'll discuss this later. Okay. One point is here that you probably already imagine is that the underlying classifier F cannot be, exactly ignored and treated independently of the whole thing. It really should be pre-trained to perform well under Gaussian noise. Well, what does well mean? Well, it means that it gives you the highest label, right, with the as high probability as possible, because you'll be needing these probabilities over here when you need this P of A. Okay, so pre-training F to perform well under the under Gaussian noise, so to give you the same label with high probability as just F of X, that's important to get good values for PA/PB so that you get better radius, okay, for fixed noise level sigma. Okay. Another question you may have is, well, another way, of course, to increase the radius. Okay, so this part here relates to this over here. But another way to increase the radius is to increase the noise. We can just increase the noise over here. Okay, if you increase the noise, of course, you start increasing this R here, okay? But it can actually reduce the accuracy, okay? We'll discuss this later. And the reason why it may reduce the accuracy is that you just have more and more, there could be, for instance, more labels that get closer in probability to, or even higher probability than the label that you have in your test set, because you just induce more and more garbage around X. So that's a point that we're going to be discussing a little bit in more detail later. So you need to be careful with increasing the noise too much here. It looks enticing to get a bigger radius, but actually you may start increasing the accuracy and even getting these two probabilities to be close, which may lead to inaccuracy in this method as we'll see later. Okay, so this is just a couple of points for you about just a reminder what the inverse CDF gives you and how to actually increase the radius, which is what you care about. And this increasing the radius we'll discuss a little bit more also later. Okay, so just you should play around a little bit with this. This is the inverse. This is the CDF of the normal Gaussian distribution with mean 0 and variance 1. And I just wanted to make a couple of quick points here, just so that you get a bit of intuition about this shape, about this expression over here. Okay. So on the first side, somebody can say, well, why is this expression not not, maybe it can even be negative, right? Well, let's play around with it a little bit, right? So if you pick some value for P of A, so if you pick P of A to be, let's say 0.6, and P of B to be 0.5, let's say 0.4, okay, then you still get a positive value according to this CDF here. So if I pick, let's pick maybe even higher values for P of A, maybe we'll pick like 0.8 for P of A, 0.6, this is the probability, the y-axis, right? And then if I do this, I'm going to end up with, for 0.6, I'll end up with some value greater than 0, and for 0.8, I'm going to end up with even higher values, greater than 0 for x, for the values that x is less than or equal to. And then I'm going to end up with a positive because this expression here, the inverse of PA is going to be greater than the inverse of PB. Okay, now what happens if you pick, just erase this here, what happens if you pick negative values here? So I pick some PA, which is small. Let's say I pick some PA, which is 0.3 over here, and I pick some probability for PB with 0.2. Well, right, let's see what happens. So let's say for 0.3, I get, let's say I get some value between -1 and 0, okay? For this expression over here, I'll get some value, let's say -0.5, okay? And if I pick 0.2 for PB, for upper bound of PB, I'm going to end up with -1, okay? So I'm going to end up with -0.5 minus -1, which is going to be -0.5 plus 1. So I'm going to end up again with 0.5, which is a positive number, okay, for the radius. So the radius cannot be negative, right? Okay, as long as this PA is greater than PB. And because the theorem requires that, remember the requirement that PA is great, lower bound of PA is greater than upper bound of PB, we require this, okay? And because of monotonicity here, we actually cannot get a negative radius, okay? All right, so this gives you a little bit of intuition. Of course, if you increase PA, okay, and you decrease PB, okay, you can see that the radius grows because of this monotonicity again, right, of the inverse CDF. Okay, so this gives you a bit of an intuition. Ultimately, that things are kosher, and so that you get positive radius, and this intuition about increasing PA and decreasing PB will be good and important for getting a higher radius, certified radius around our point X, which is what we care about, with a fixed sigma, fixed standard deviation, fixed noise. Okay, a little bit, few more points here, which is important. Okay, I already mentioned this, that the certified radius here R that we obtain, okay, can grow when you vary the PA/PB, but an important point is that the certified radius may differ between different inputs X, okay? For different input X, you may end up with different certified radiuses. And the reason why you may end up with different certified radiuses is because these PAs, and PBs for different points are different. And so your radius that you get may be different for one X versus another X, okay? Now, naturally, this gets to the question of how do we actually, given that we get different radiuses may get different radiuses for the certified radiuses for different points, okay, and still remember we're talking about L2 norms here. In the exercise, there's going to be an exercise which shows you how to convert the L2 norm to the L infinity norm. So if you get bounds for the L2 norm, you can get bounds for the L infinity norm, okay? So don't worry so much about the L2 here. Now, because for different X's, we may get different radiuses, the question is how do we actually measure the certified accuracy of our G of X, of our model? And so what you do is the following, okay? So let's say we pick a target radius T. So if you remember in our discussion so far, so maybe in the case of CFAR10 would pick a radius of 8 out of 255. Or in the MNIST, would pick a radius t equal to 0.1 or radius t equal to 0.3. And all we're going to do is we're just going to count the number of points in the test set. We're just going to look at those points in the test set whose certified radius, and remember they may have different certified radius, is greater than or equal to t. And if it is greater than or equal to t, we're going to count the point, right? We're going to count this point and further the point, because we also care for the correct label in our test set. You know, we want the predicted label CA that we get right here, the CA, okay, that G predicts. We want to make sure that this matches the label in the test set. So if the certified radius is greater than or equal to t for the given x, okay, in the test set, and the C of A, the predicted label that G predicts for x, is the same as in the test set, we're going to count this as a successful point. And if either of these two conditions don't hold, we're not going to count it as a successful point. So that's how we can compute our certified accuracy percent. Okay. Of course, if you get higher and higher radiuses as t, there will be fewer and fewer points which actually satisfy this condition, that our certified radius is greater than or equal to t. Okay. Now, the standard accuracy is just, we don't care about the certified radius. So basically it would be t equal to 0, but we still, of course, care about that the label matches what's in the test set. So you can just take that procedure and just instantiate standard accuracy by taking the t, the target certified radius being 0. So we can that way compute our standard accuracy. Okay. Okay. So this gives you a little bit of a understanding that different labels, different inputs may get different certified radiuses, and then we need to take that into account when we're computing the certified accuracy and the standard accuracy. Okay. So now we discussed this idealized setting where we can compute the PAPB or the lower bound on the PA and the upper bound on PB, and we have the true label C of A. Okay. In practice, that's difficult to actually get this, or impossible essentially. So doing this analytically with solvers like Psi or some other exact inference solvers will not scale. And so what we're going to be doing is we're going to be resorting to sampling for computing these probabilities, specifically PA, and the best label, some approximation of C of A. Okay. And the nice point here will be that this, even though it's sampling, it's still going to give you some useful statistical guarantees on these probabilities, and then on the entire guarantee on certified radiuses that we obtain from the theorem. Okay, so let's start by looking at the certification procedure, and I have taken the certification procedure from the paper as is. Okay. And let's look at it and understand it a little bit more. So now we're going to be wanting to compute, we're going to want to certify a single sample here. So let's see what the parameters are here. And then of course, we're going to compute certified accuracy. We're going to be, certifying each of the points in the test set. Okay, good. So, right, so now let's see what the parameters of the function certify are. Okay, so what we have here is we have F, which is the base classifier. We have sigma, which is the noise that we're going to introduce. We have X, which is the input image. And we have N0, which will be some number of samples that we'll take. We have N, which is the total number of samples. And we have alpha, which will be used to capture the confidence, right? Okay, and so one thing to note here before we proceed into the entire function of the certification is that this part over here, okay, this part over here is essentially going to determine the top class of the highest class, the highest label from the samples that we take. and we're just going to you're going to take sampling twice. In the first one, we're going to determine the highest label, and in the second we're going to determine we're going to avoid this selection bias. We're going to be sampling with a greater number of samples and 0. Okay. So let's take a look at what this sample under noise does, which is pretty much what you would expect to happen here, right? So what we have is the sampling under noise is going to evaluate the base classifier f at a bunch of points here, x plus epsilon of I, where each epsilon of I is the sample noise introduced by sampling the isotropic Gaussian over here. Okay. And this will return a dictionary, a map from the labels to their corresponding counts. All right. So this is what this does. So it does n samples. So here we're going to do n0 samples, and here we're going to do n samples. All right. So once we update the samples, we need to decide what is the probability of this top class that we've observed, and what are the lower bounds on this probability, and then decide whether to return this label or not. So let's look at this a little bit. Okay. So what we have here is we have the following function, this lower confidence bounds function, which takes the total number of samples that you have where you predicted the top rank class CA hat, the total number of samples, and some confidence, some probability here. So typically alpha is very small, something like 0.001. And so you end up with essentially a very high confidence on your lower bound prediction for the probability A of the label C of A hat. So let's just look at this function for a second. So what does it do? So assuming that you have a bunch of independent samples n, okay, and some unknown probability of success p, and assuming that this number of successes that we saw, this counts of CA hat, k here, is sampled from this distribution for some unknown p that we don't know what it is, what this function will do, it will return a lower bound on the probability. The lower bound will be PL, right, such that this PL less than or equal to P is going to hold with some high probability 1 minus alpha, and if alpha is like 0.001, which you typically take, you then end up with like confidence of 99.99%. All right, and so what it does is it finds a lower bound here on the true probability P of A, which is what we want to have from the samples that we've observed with high confidence. Okay. So so there are many ways to get this lower bound. There are many different methods, right, to compute the confidence interval. The paper uses this Klopper-Pearson bound, but there are different ones. So now once you have obtained this lower bound, you need to decide whether to make a prediction. Okay. So let's take a look at that. And so what happens here is you decide to make a prediction when your probability is the lower bound is greater than 1/2, because then you know that the label that you are predicting, the C of A hat, is going to be you're going to be confident in predicting this label. Okay, its probability is going to be greater than any other probability. Okay, and then interestingly, you're going to predict this with the following certified radius over here, which we're going to derive in a second. Now, to derive this radius and to anyway obtain to invoke our theorem with the guarantees, to plug in these guarantees, that robustness guarantees theorem that we looked at earlier, what we're going to be doing is first we're going to we need the P of A lower bound of P of A and an upper bound of P of B. So what we're going to do is let us set the upper bound of P of B to be 1 minus the lower bound of P of A. This is not a tightest bound possible, but it's certainly an upper bound on P of B. And now, of course, because the lower bound is greater than 1/2 from here, we know that, okay, that's only one when we make a prediction. We know that the upper bound on the P of B is less than 1/2, and therefore we know that the lower bound of P of A is less than or equal to upper bound of P of B, which is a condition to apply our theorem. So we can now instantiate this theorem because of this condition here. Okay, so let us do that. Now, if we instantiate this theorem with a condition, what we're going to get is we're going to obtain the following radius. Okay, we're going to obtain, we just plug in this 1 minus P of A lower bound here for upper bound of P of B. And we're going to get the following radius, right? We just by plugging things, so plugging here the upper bound of P of B, and these two are equivalent, minus the inverse CDF of the normal Gaussian is the same as the plus of the inverse CDF with the P of A. And then we're going to end up with the following radius over here, okay? And so basically, because the condition of lower bound of P of A being greater than or equal to the upper bound of P of B, and taking that value for the upper bound of P of B, we can now get the certified radius and get our guarantee from the theorem. Now, if we have a probability of the lower bound which is less than or equal to 1/2, then we're going to abstain. And if we abstain, of course, in certification, this is going to be counted as a wrong label from the test set. So it's going to be an incorrect prediction and our certified accuracy will drop. All right. So what is the final guarantee that we get from the theorem here? Well, what we get is, let's kind of read from here. So if certify succeeds, so if we actually return some CA hat here, okay, with this radius over here, that's what it says, then the smoothed classifier, okay, is going to produce this label that we return. It's going to be robust in this label with the following L2 radius. So the radius that we return, okay, is our X is going to be robust in that radius and return this CA hat over here, okay? So this is going to hold with probability 1 minus alpha. So our radius is going to be certified essentially. When we make a prediction for that radius, it's going to be certified with probability 1 minus alpha, which is going to be very, very high. Okay, so this is a theorem. Okay, so when we make a prediction actually about the radius, we are confident in that this is actually the very confident this is actually a certified radius here. All right, a couple of points to be made here is that of course this whole thing deals only with robustness, right? It doesn't deal with the labels in the test set. And so it doesn't deal with labels in the test set. And so the prediction may actually be that you make here, the C of A may actually be incorrect in the when compared to the test set label for the input X, right? And so, right, that's what we say. So this an output that we predict C of A hat may not necessarily be correct, may be different from the label that you have in the test set. All right. And so there are several reasons why now one may obtain actually this incorrect label in the test set. Okay, so we're going to look a little bit that, and just a note here that incorrect label also includes these abstentions over here. Okay, so let's look at this a little bit. What are the reasons for why you may actually obtain a prediction which is different than what you have in the test set? So let me take a look here. So what we have is we have the following reason. This is reason number one, is as we increase the noise, the sigma, it is just more likely that the perfect classifier G of X returns some C of A, returns some class, which is not what you have in the test set. So you can see that here with these images, right? As you increase the sigma from 0, 0, 2, 5, 0, 5, and 1, and so on, you actually get images which actually may be difficult to, you don't know what the label here is. This image here, like its label may be different than what's actually in the test set. Okay, so this is one thing. But now, even if the perfect smoothed classifier produces a prediction which is in the test set, okay, it's in the test set, it's the same as the test set. Okay, there are a couple of other reasons why you may actually get a well, you actually may get a different label than what's in the test set. Okay, so there's actually two sub-reasons here. So one is if this N0 is small, so typically happens over here, when the N0 is small, then, it's small number of samples, you may actually end up with some C of A here, C of hat, which is different than the C of A. And when you then correspondingly, you compute the this probability, this lower bounds on the probability here, then if you're doing this, then you may you're likely going to end up very likely with something which is not greater than 1/2. Okay, so that can happen. And further, it is possible that this can happen also because this true probability PA and the next best probability PB, let's say, okay, are very similar. Okay, so if they're very similar, you again may end up with something which is different than even if you have a good N0, with the CA hat is different than the C of A. So then again, you'll end up with some confidences here that are quite low. Okay, and so you're going to end up with confidence quite low, and in both of these cases, you're going to, you're just going to abstain. Okay, so you may get either if the sigma is large, right, the noise is very large, you may just end up with a prediction which is some C of A, which is different than what's in the test set. That's reason one. Reason two, even if the C of A, the perfect C of A, is the same as in the test set, your N0 may be small, or your probabilities are very close, the PA and the PB, the next best probability, and so you'd end up abstaining here because you wouldn't have so much confidence in your prediction. Okay, so this is what can happen. All right. Now let's look at a little bit here. How's this? So you may abstain. So this is something that I show in this table that's a little bit instructive when you're actually computing the certified accuracy, to see a little bit the effect of this sigma on the certified accuracy, on the natural accuracy, and this trade-off. So in this table, what you have is this ImageNet table, and it was equal to 100,000 points, 100,000 samples. And what you do is that each entry is essentially the percent of images in the test set. So in this case, this is the ImageNet images, right? Which have a radius, probable radius, which is greater than or equal to R. Okay, radius is greater than or equal to R. So whatever the R is, let's say we take this 1.0. And the label that the CA hat label that you predicted is the same as in the test set. So like, for instance, here, if we take this 37%, this would mean that 37% of images had a provable radius greater than or equal to 1.0 than 1, and it was the correct label. Okay. So there's just a couple of points that you may notice here. First of all, as the noise increases here, typically as the noise increases, you're able to prove more. I mean, if you look at something like over here to 0, for a larger radius, remember that sigma controls the radius. So for a larger radius, you would not prove anything here. Nothing would be robust and correct here with a large radius, but here you get 19% over here. So you get more robust, you can prove larger radius, but your natural accuracy also decreases, which is the, remember that we instantiate the natural accuracy when R is equal to 0, okay? And so this is kind of what you would expect to happen. So you'd have the standard trade-off between the, as the noise increases, the standard accuracy drop, but the certified radius that you can prove increases as well, right? So this is the kind of accuracy trade-off that we discussed before when we discussed adversarial training. Okay, so just to reminder again that all of these results are statistical in nature with this 1 minus alpha, which is 99.99% for the certified radius, and not deterministic, so they hold with high probability, okay? But not 100%, let's say. Okay, so this is just a couple of points on the sigma, and predicting the wrong label could be again due to very large sigma, and just the CA perfect label is wrong, not what's in the test set. But it also could be even if the perfect CA it can be predicted. In theory, it could be predicted by the perfect classifier. It just could be that when you are when you are sampling your you actually ended up with reason 2, and then you were abstaining. So there's a couple of reasons why your numbers here may not be 100% here, or like you have incorrect predictions, which we discussed on the previous slide already. Okay, and if you go back actually to the previous discussion, you know that to increase this for a fixed sigma, in order to increase this probability, so you may have to take more samples. Okay, so this is actually one question. If you actually fix the sigma, the noise here, how can you improve your radius that you're actually proving? And we know that to do that, you need to improve this lower bound on the P of A. Okay, because that's the function is monotone. So the greater this value here is in the red, the larger your certified radius will be. Okay. Now, even in the extreme case that your F, you've trained your classifier so that it is so good, so that all things are always classified to C of A by F. So things are always classified to CI hat by F. Increasing this number of samples actually will only slowly grow the radius that you get. So let's plot this a little bit here. Okay, so let's plot this. So what we have, even in the best case scenario, we've always classifies to C of A, get to the perfect label, everything is good, with a confidence 1 minus alpha. A tight lower bound for P of A that you can get is alpha of 1 over n. So that's quite a tight bound. Okay, and if you plot the resulting radius here of this resulting radius function, for alpha equal to the usual alpha we take like 0.001, and the noise being 1 as in the normal Gaussian, you see that the increasing this number of samples only slowly grows the radius. So increasing the number of samples and only slowly grows the radius. So this would be like one disadvantage of smoothing, as it requires many points here. Okay. All right, so this is a couple of points here about the radius. Okay, so regardless, once you have certified the classifier on the test set, whether you did this exactly, whether you did this with sampling, we discussed sampling so far, you actually need to use this classifier at the inference time. So again, we're going to resort to sampling because we cannot evaluate the classifier exactly. So let's just see a couple of points here. How do we actually use it at inference time? So just even before we discuss the details, one thing to notice here is, again, we have the same parameters as before. Okay, and again, we're sampling. So one thing to notice that you need additional work at inference time. So more work will be needed at inference time, which can actually be potentially expensive. Okay, so this is something you don't need for the convex methods. You just run your point through. Okay, and so let's look at this function we already looked at. We are taking samples. And so how does predict work? So it just samples and it just takes the top 2 labels and their corresponding counts over here. Okay, and now the interesting part is this decision-making procedure over here, which is going to decide whether you want to make a decision or not. Okay, so this is one question. And so what happens here is that we need to decide whether to make a prediction or not make a prediction like we had in certification. Okay, but there we cared about these probabilities and getting larger probabilities because that would give us a higher certified radius. While here we just need to decide whether we are confident now in making prediction. So one way to do this is to employ this no hypothesis test. So let's look at the no hypothesis. So the no hypothesis says that in this case, that the true probability of success of a Bernoulli trial is Q. So this is our hypothesis, and we're going to aim to reject this hypothesis, okay? So if we actually instantiate the no hypothesis in our case, okay, if we instantiate it, this is going to be that the true probability of success, that is of F returning the CI hat, okay, is going to be Q equal to 0.5. So we're going to instantiate Q with 0.5. So essentially it would mean that the classes are indistinguishable. The CA class and the CB class, if you have binary classification, or the CA class and the sum of all the other classes that you have there. Okay, so this is one test that we make, and we're going to aim to reject this hypothesis. Okay, and so there is this function here, binomial P value, essentially returns you a P value. Okay, P value probability, some confidence, best to think of it as confidence of the null hypothesis holding, okay? And so this function is going to evaluate this, it's going to be evaluated on n samples over here, statistically independent samples with I successes, just like we did before when we did certification. And it's going to give us some p-value, okay? And we are going to reject this p-value, okay, the p-value that we get. We're only going to, we're going to check this p-value, whether this p-value is less than some threshold alpha, so some low value like 0.001. And only if it is less than or equal to this value, alpha, then we're going to make a prediction. We're going to reject the null hypothesis. So we reject the null hypothesis only when the alpha, we're less than this value, the small value of 0.001, let's say. Otherwise, we're going to accept the null hypothesis and essentially say, well, no, the null hypothesis holds, so we're going to abstain, okay? So as I say in the next slide, I think, this is what I said already, but if you have a small alpha, if the alpha is small, okay, it's a small value, then you more often accept the null hypothesis and abstain, okay? Because you are trying to be very, very sure when you're rejecting the null hypothesis, but you'll be more confident in the prediction when you're actually making a prediction, okay? If the alpha is higher, if you get bigger values of alpha, then you'll be make predictions more often, but you may make more mistakes. Okay, so this is what happens at inference time. And the main thing here is that you have to do work by having more samples and than just a single sample like we have in the normal inference. Okay, so a couple of points about the guarantees that you get. So the guarantees that you get here is that, so we care in the case when we are not abstaining and we're making a prediction. So the probability that I'm not abstaining and making the wrong prediction, the joint probability of these two events happening, right, is going to be at most A, at most alpha, most this alpha over here, okay? So we're going to return the wrong class, Ci hat not equal to C of A, okay, with probability at most alpha. And then, okay, so this is not, we know when we are wrong, like what is the probability essentially of being wrong. This is a small proof sketch here, how it goes. So this is the probability that we're interested in understanding. We're making the wrong prediction, we're not abstaining. Well, when you expand the formula for the joint probability, you get the following expansion. This is standard. And if you drop this probability here, you're just gonna get an upper bound over here. You're going to get an upper bound over here. Of course, if this probability is actually very small, right, then you're not going to have a very tight upper bound, or not very tight upper bound over here. But nonetheless, this is an upper bound, and there is a related work there's a paper that was updated in 2019 in statistics, which shows that this bound here, this probability here is alpha. So the whole thing is going to get bounded by alpha over here, all right? And so we get what we wrote in the previous slide already. You're welcome to look at this paper and published in Annals of Statistics and to see what is going on. Okay, so this told you a little bit, we discussed a little bit what are the certification guarantees. So what are this 1 minus alpha probability on getting a certified radius. And then, so that's one thing. And then the second one is what is the probability on the making an incorrect prediction at inference time. Okay, so this told you a little bit about the guarantees of this method. Okay, one thing that we recently did, and it's actually following the spirit of the course of always discussing something that is presented in the same month as the lecture, and we generalized this idea of smoothing to richer transformations, like geometric transformations such as rotations, translations, and so on. So essentially, you're going to have a base classifier f, just like before, but now instead of just adding input and noise to the input, you are going to have these transformations that looked at before, where alpha is the parameter of the transformation. And then we're going to construct a smoothed classifier just like before, except that here, rather than adding just noise to the directly to the input X, we're going to add noise to the parameters of the transformation. So this standard smoothing can just be actually instantiated by just the following equation. So this function psi is essentially just X plus epsilon, right? But in our case, this function psi could be geometric transformations like rotations and translations together with interpolation. So you would essentially be adding isotropic Gaussian noise to the parameters of these transformations, and thereby certifying with some high probability that the geometric transformation performed in input X is correct. It's robust. And that's exactly what we did. The isotropic noise is the same as before, the isotropic Gaussian. The one caveat here is that to instantiate this, to use our work, you would need to have this requirement on the composition of the transformation. So for instance, if you have rotations, angle A and angle B, angle alpha and angle beta, you would want that they decomposes, okay? And this is actually quite tricky because of interpolation. So you can look at the paper to see why this is tricky. But generally, we obtain the same guarantees as what I described so far during certification. Okay, but we actually generalize this a little bit further to something called individual guarantees and more relaxed distributional guarantees, because the setting is a little bit more complex than just adding noise to the input X, right? We also adding noise to the parameters of the transformation, okay? But this kind of ties down our lecture to the previous cases we considered with geometric certification, where we had a base classifier, and we just did geometric certification in previous lecture, like rotations, translations. And now here we have the same idea, but now done with the smoothing method, okay? So I encourage you to look at the papers, both this paper and the randomized smoothing paper and the prior works upon which it built to get a further understanding if you're interested in this space. Okay. So in summary, what we did in this lecture, we introduced randomized smoothing, which is a method that constructs a robust classifier by introducing isotropic Gaussian noise. And this comes with guarantees, statistical guarantees that on the robustness of the radius that you obtain. So we obtain the L2 radius, but in the exercise, in the course, you actually see how to obtain a L infinity radius from the L2 radius. One benefit of smoothing is that it scales to larger networks because you don't do this convex propagation, you just do the sampling, okay? Of course, you may need many, many samples to, as we discussed, to actually get good radiuses, okay? Another point about smoothing is that it relaxes the standard deterministic guarantees into the statistical guarantees with high probability, like let's say 99.99%. But, right, it may require also inference at work at inference time, which convex methods do not require this, right? And we also show the classic trade-off, just like we did before when we did adversarial training between accuracy and robustness here as well. Okay, and we very, very briefly discussed the potential generalization, actual generalization that we did this year at NeurIPS 2020 to different properties, okay, which can be quite involved to richer properties, essentially, like rotations, translations, and other transformations. So I hope that you found the lecture interesting and this and useful, and this method of randomized smoothing. Another point in the space of the certification methods that we looked at before. So now you know about the deterministic certification method based on these convex relaxations, mixed integer linear solvers, and the randomized smoothing, which is a statistical certification method that comes with high confidence. So when you're given the task of certifying machine learning models, you have a greater toolbox to choose from. So I hope you enjoyed the lecture, and see you next time.